Okay, trying to take a look at some more common tangents and then being able to draw them on your own. For example, if I have these two circles that actually do not intersect, even though they don't intersect, there's a couple of common tangents for them. So if I draw a line that intersects each of those circles and only one point, this line, let me call it line K, is tangent to this circle, call it circle C, and then this circle, circle D. So this is a common tangent because it's tangent to both of those circles and both of those circles share it. And even more specifically, this tangent is outside of the two circles, so it's a common external tangent. Okay? It's external because it's outside. The opposite of that would be an internal tangent. Okay? But that's not the only common tangent that these two circles share. Here's another common tangent. Call it line L. So line L intersects each of those two circles in only one point. It's tangent to circle D and it's tangent to circle C. So that's a common, again, external tangent. Okay. If I had those two circles or just two circles intersecting in a single point, there's a common tangent between those 2 points. That common tangent would be basically right in between those two circles. In this case, the common tangent, even though you might think, well, it's outside the circles, this is an internal common tangent. And the reason why it's an internal common tangent is it intersects the segment that joins the two centers of the circles. So here's the two centers. This line, call it line P, intersects that segment. So it's a common internal tangent. Okay, both of these lines right here are external tangents because, one, they're outside the circle, but two, they do not intersect the segment that joins the two centers of the circles. And there's a couple of theorems that go along with circles as well. The tangent line to a circle theorem. So the tangent line to a circle theorem, let's say line L is tangent to circle C. Not only does line L intersect circle C in only one point, but if I draw a radius to the point of tangency, then that radius is perpendicular to that tangent line. That's the tangent line to a circle theorem. And then there's theorem 10.1 written out as a conditional statement. Now in a plane, a line is tangent to a circle if and only if that line, so that tangent line, is perpendicular to the radius of the circle drawn to the point of tangency. So this point right here, I'm going to call it point P, is the point of tangency for line L, and then the radius, CP, is perpendicular to that line of tangency. And theorem 10.2, the external tangent congruence theorem. So if you have a point that's outside of the circle, that's an external point. If I have a segment, so besides a line, a segment could be tangent to a circle. It would just intersect that circle in one point. But if I have two tangent segments from the same external point, call this segment or tangent AB, this tangent BC. If they're to the same external point, then those two tangent segments are congruent. So AB is congruent to BC. And there's the external tangent congruence theorem written out. Tangent segments from a common external point, which in this case is B, are congruent. AB is congruent to BC. So if we knew the length of AB, 6 units, then the length of BC would be the exact same, 6 units.